Hello, my name is Johannes Adam. Would you like to know the temperature of your board before prototyping? Perhaps this simulation tool called TRM is what you are looking for. Let's show the setup. Suppose we have a layer stack. Suppose we have components. Suppose we have currents in and out, heat sinks and other cooling conditions. We can create a model that calculates current density, heating by current, heating by components, resulting in temperature maps for each layer and each prepreg. Let us do some example based on the DesignSpark chip kit board. What I did is I just used the standard output features, say exported Gerber files, exported drills as Excellon, and components by IDF files. After the output, we have to import these files into the simulator. And I've prepared some stuff here. First we have to know the size of the board, say the length in X and the width in Y. We have to know the default materials for the conducting planes and the dielectrics. And we have to know the smallest features that have to be resolved, either this most narrow tracks or the most narrow insulations. The next step is to build the layer stack. You see we have a 4-layer board which results in 7 calculational levels. The level 1 is the layer 1. We import the Gerber file by just clicking on Expose. This is a picture of the Gerber input, and after a while we get a calculatable map of the copper distribution. So this procedure has to be done for each layer. And we could modify now the thickness of the layers as we like to have it. I could show you the result of the other Gerber files. This is the internal layer 1, the internal layer 2, and the bottom layer. Next step is to drill holes. For that purpose we use the Excellon output from DesignSpark, and of course this has to be converted, but before we convert we define some technical data. For example, is it a through hole or is it a blind or buried wire? What's the thickness of plating and the material of plating, is it filled or not filled, for example. If you have several technologies in your board, you just add more of these lines. A control plot of the Excellon data. Now these circles are converted into effective drills because the 20 mu plating is not resolved geometrically. Instead we build a physical model for each plated drill, and this is represented by the squares embedded in the circles. Now this is done. We have 349 holes. Next step is to create components. There are several ways doing that. For example, we could start interpreting the silk screen again by importing the Gerber and then using this as a background template to draw components manually. Or we could use the IDF files for component creation. For that we have to import the board file, and the software will ask for the library file. They are called IDL here. And this is dumped into a so-called mount file we will use the next step. But here are some warnings. The component height is not available in the file, so it is taken a default of 1.11 millimeters. Finally, we set up the laboratory situation. For example, we have 20-degree ambient air temperature and free convection. If we have other conditions inside enclosures, we just have to modify these numbers, or if you don't know what a heat exchange coefficient is, you can use this assistant. I did already import the IDF export. This came via a mount file. This mount file is already imported, and I could visualize it graphically. And on the background picture of the top layer or the background picture of the bottom layer, the rectangular stuff is the IDF import. I can modify each component, for example IC2. IC2 got another color, and it got some values, for example 2 watts. IC1 got 1 watt. R34 got 0.2 watts. And I created some current data. For example here, a pin with plus 4 ampere feeding current in, and another pad defined by minus 4 ampere taking current out of the board. You will see those sites are not connected on top plane, but they are connected on top, on bottom, by a drilled hole here. This is taken into account by our input. All this data can be controlled and modified. In this list you have access to any field in this table. Last step is to run the simulation, or in other words to do the laboratory test. Let's click on Start Calculation. The first step, of course, is reading and analyzing the input data. And we start with calculation of the potential field or the voltage. The voltage will result in a current density. This current density is creating heat, so-called Joule heating. The Joule heating of the tracks is added to the heat by components and will be used to calculate the final temperature field. All these calculations are done iteratively because we have large systems of equations to be solved. We could control the convergence and see how it runs. The important issue is that the residual should drop by about 2 decades from beginning to the end of the calculation, and the maximum value of our variable should be constant over a sufficient number of iterations. So the voltage loop is done within 50 seconds, and the electric power of our setup is 0.5 watts. There's an automatic creation of a picture result gallery with voltage values and current and temperature values. We look at them. This is the voltage map of layer 1, internal 1, internal 2, and the bottom layer, and the difference between this voltage value and that voltage value will be the voltage drop in DC. Alternatively, we could look at the current distribution, for example, in that way. In the background, the temperature loop has started. And we have to wait for, I guess, 2 minutes until the final result will be reached. Finally, the temperature has converged and gives a maximum temperature of 90 degrees Celsius, done in 3 minutes. Temperature maps are automatically created, and we just look at them. "90 degrees is reached here. This component comes with 70 degrees. Here we see the heating of the trace, the narrow part, and almost no heating in the wide part. Transient calculations are available either just as heating curves or with Excel import of stepwise current or power values. If this is interesting for you, just contact us and we will allow for a test installation. Thank you very much.